Hello everyone and welcome to my second ever math video on this YouTube channel. So as you saw in the title, I found the integral of this expression w of x dx, and today I'm going to show you how. So for those of you who don't know, this is a Lambert W function and it's defined as this. W of x e to the x equals x. So for example, if we have w of 2e squared, the answer is going to be 2. So some examples: w of 0 equals 0 because 0 times e to the 0 equals 0, and w of negative 1 over e is equal to negative 1 because negative 1 times e to the negative 1 equals negative 1 over e. Before we get into the integral of the w function, we first have to solve this integral of x times e to the x. And you can solve it with integration by parts. I'm sure it's pretty easy, but I'm going to show another way of solving it. So first, this x can be rewritten as natural log of e to the x, because that's the natural log and the e will cancel each other out. So we can rewrite this integral as the integral of natural log of e to the x times e to the x dx. Now we can make a u substitution. We can say u equals e to the x. And now this becomes the integral of ln u. And now if u is equal to e to the x, then du, the derivative, is going to be equal to e to the x dx, because e to the x doesn't change when differentiated. So this part is just ln u, this part is just du. So we can integrate ln u du, which is u times ln u minus u plus c. Now we have this integral, we can just sub in e to the x into all of the u's. So what we get is e to the x times ln e to the x, they cancel, so you just get x, and I'm going to write the x here because it's more pleasing. And then minus u is just minus e to the x plus c. So the integral of x e to the x dx is x e to the x minus e to the x plus c. And if you differentiate that, you'll see that you get x e to the x back. So that's the first integral we have to do. Now for our next step, let's have a look at these two graphs. This is the graph of y equals x times e to the x. It asymptotically approaches 0 on the negative side and then takes a dip and goes up by a lot. This is the graph of y equals w of x. As we mentioned, these two graphs are inverse functions, so we can just flip one as a mirror at y equals x line, and this is roughly what it's going to look like. You may notice that it stops right here, even though this graph continues forever, because if we continue here, we'll have two values for one x value, which is not allowed in inverse functions. So this is what we want. From the graph y equals w of x, we want to find an expression for this area under the graph. So if I draw this rectangle, I can express the area from 0 to a certain number x with this shaded region, and I can also draw this rectangle with length x and height w of x, because this is what the function is doing. So how can we use this to find the area of the shaded region? If we can find the unshaded region of this rectangle, we can actually use it to find the shaded region. And as I mentioned before, these two graphs are a mirror image of each other at y equals 1 over x. So this area is actually equal to this area, because this is the same w of x, and we just flip the entire thing on y equals x. And if you look, this area and this area actually represent the exact same thing. And this w of x is just the same w of x, and we're still looking at this x as our variable. So now we can calculate the area of this rectangle and this unshaded region. So we just subtract the unshaded region from the rectangle and we get the shaded region. So that's how it's going to go. This rectangle, we know its dimensions, so the area is really easy. It's just x times w of x. And this area is, as I mentioned, the same as this area, which can be represented as this integral from 0 to w of x. And this is actually the exact answer that we need. This tells you all the information you need to know to find this area. But we're not done yet, because we can solve this integral first. In other words, the integral of w of x dx is equal to x times w of x minus the integral from 0 to w of x of x e to the x dx. And now we can just solve this integral as we usually would, because it's even a definite integral, so we don't even need to worry about plus c. So first, we plug in w of x for all the x's. This is what we get. But notice, w of x is the inverse of x e to the x. So, in w of x times e to the w of x actually just gives you, this whole part just gives you x. Because w of x is by definition the number that when multiplied by e to the power of itself gives you x. And now this part is actually really similar to this part, it just doesn't have the w at the beginning. So if this part is equal to x, this part is just equal to x divided by w of x. Because all we've done to get from this to that is just get rid of this w. Now we're done with this part, we just have to plug in 0, and this is a lot easier. We just plug in 0 into all these x's, and we get 0 times e to the 0 minus e to the 0. 0 times anything is 0, so it doesn't even matter what this is, and e to the 0 is 1. So our final answer is x minus x over w of x minus 1. This is almost the answer we need, but just not quite. Now we have all the information we need. We know the area of the rectangle is x times w of x, and we know this unshaded region is x minus x over w of x minus 1. So all we need to do is our final integral is just equal to this expression minus this expression, and I'm just going to write it out. And from there on, it's just simple algebra, so you flip all the signs of this expression because of the negative. And the last step, this plus c plus 1, 1 is also a constant, so this could be the new c. So this is actually our final answer. So that's actually it. If you want to prove this, you can take the derivative of this expression, and you should see that you will get the w of x back. And I did check it, it works. And that's pretty much it for the video. Really appreciate it if all of you guys press the subscribe button, because I did spend a lot of time and effort on this video. Let me know if you want me to do more math videos, even though I'll probably just keep doing them whenever I have something really cool like this, or like the imaginary numbers one I had a few months back. And that's it. See you later.